Hey guys, welcome back to chapter 13. What we're going to dive into now is something called colligative properties. This is really the heart and soul of this chapter. This is really the fun part. So let me pose a few questions here. Why do we throw salt down in winter? So when the roads or when the weather's getting cold, they're worried about the roads getting slick. Why do they always put a layer of salt down before the snow comes? Or why do we throw salt in front of the doors of businesses before the snow comes? And is salt really the best thing to use? What's the purpose of antifreeze? So we put antifreeze in our cars. Why do we put antifreeze in our cars? What purpose does it serve? And actually, it serves a dual purpose. So we'll talk about what purpose it serves. And then think about being stranded at sea. So one of the major causes of loss of life when stranded at sea is dehydration. But you're surrounded by water, so that kind of seems counterintuitive. So why can't you just drink the seawater, the salt water, to survive? So by the end of this chapter in the next few lecture series, we'll be able to answer all of these questions using colligative properties. So colligative properties is a value that depends on the number of solute particles, not what they are. Okay. So what we're going to look at with colligative properties is how different things change. So how properties of a solution versus properties of a pure solvent change. And the change depends not on what we put in there. It doesn't matter what we put in there. The change depends on the number of solute particles. So that's really one of the big take-homes with colligative properties. Number, not what it is. Okay. The four colligative properties that we're going to talk about is vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. In lab, we're going to be exploring this freezing point depression. So that'll be the one that we get to explore in lab. But we're going to have all four of them that we're responsible for on the exam. Okay. So the first one that I want to talk about is vapor pressure lowering. Okay. So remember what vapor pressure is. Vapor pressure is the pressure exerted by a gas or a vapor when a dynamic equilibrium is reached. So we put some sort of liquid, solvent, if you will, but some sort of liquid into this flask. We close the flask. It's a closed system. At some point, some of this liquid is going to change state. So it's going to evaporate or vaporize. And it's going to be released as a gas up here. Remember, we're overcoming intermolecular forces in order for that to happen. So it's going to be all an up process. We're going to create vapor. Then we're going to reach that dynamic equilibrium. Some of this vapor is going to condense back down to liquid. So we're going to have condensation, vaporization happening dynamically. But the rate is going to remain the same. So when we measure the pressure exerted by the vapor, it's going to remain constant. Okay. So what we're going to talk about now is how does the addition of particles affect the vapor pressure? So if I looked at a pure water sample, and then I opened it up, added a few salt particles, closed it, how would that affect the vapor pressure? And then we're going to answer, why does it affect the vapor pressure? Okay. So before we talk about that, let's think about the process of vaporization. Okay. What particles are available to vaporize? So we're not talking about boiling. We're just talking about at room temperature. What particles are available? Is this particle down here available? No. Particle in here available? Nah. Only the particles that are at the surface of this container are available to vaporize. Okay. So when we add a solute into this beaker, the rate of vaporization goes down, hence vapor pressure lowering. We kind of alluded to this. So the rate of vaporization goes down. Why is this the case? So with the addition of a solute, now that solute and solvent are competing for space up here at the top. So where the blue particles would have had, 20 available particles to vaporize, now they only have 16 particles available to vaporize because these solute particles stole for the positions. Okay. So with the addition of a non-volatile solute, this reduces the rate of vaporization or decreases the amount of vapor. If there's less vapor, then there is a lower pressure, right? So less vapor, less particles to register a pressure, so a lower pressure, vapor pressure lowering. Okay. This idea of a non-volatile solute, for our case and purposes, the solute will always be non-volatile. Things are a little bit different if it's volatile, so it also has the ability to vaporize, but we're going to assume non-volatile, so we're going to assume the solute does not vaporize. So once we have these solute particles that are up here taking up spaces, we're going to have less particles that are vapor. Eventually, we'll reestablish a new equilibrium. So eventually, we'll reestablish that dynamic condensation, vaporization, condensation, vaporization. But what we'll notice about that new equilibrium is that the pressure will be registered as lower than when it was just a pure solvent or just a pure liquid. So it does reestablish equilibrium, but that equilibrium is at a lower pressure, a lower number. Okay. So that was the qualitative look at vapor pressure lowering. We can quantify this process, right? We can quantify the change in vapor pressure. So the law that we use is Raoult's law. So the vapor pressure of a solution is proportional to the mole fraction of the solvent. So this idea of mole fraction really simply is just another unit of concentration. That's all mole fraction is. So I'll introduce the idea of mole fraction as we work through these solutions. So here is the formula for Raoult's law. So the vapor pressure of the solution, so P solution is vapor pressure of the solution, is equal to, this is mole fraction, so the mole fraction of the solvent times the pressure of the solvent. So remember this little degrees symbol next to it is just at standard state, so standard pressure, temperature, that kind of standard situation. So this would be the vapor pressure of, let's say, water by itself. And this would be the pressure of the solution. So after I put a particle in there, now what's the pressure of the solution? Okay. So pressure of the solvent times the mole fraction of the solvent gives us the new pressure. Okay. And that new pressure should and will be lower. Okay. Mole fraction. So let me just go ahead and address that here. So mole fraction of the solvent. So this idea of mole fraction of the solvent is going to be, on top is going to be the number of moles of solvent okay, so this would be, let's say, moles of water that are present in the solution. And on the bottom is going to be the total number of moles. So that's going to be solvent plus solute. Okay. So the number of moles of solvent, whatever the greatest proportion is, divided by the total number of moles of stuff or particles in the solution. So that's going to be the moles of the solvent particles and the moles of the solute particles added together. Okay. The number on bottom will always be bigger. The number on top will always be smaller. Okay. So this will always be a decimal. Okay. So an ideal solution. Solutions that obey the Raoult law. And an ideal solution is going to be one that works best when the solvent and solute have similar intermolecular forces. So in chemistry, specifically general chemistry 1, we deal with ideal solutions. If you've ever taken a physics class or a physical science class, you would always read this silly, like, ignore friction. And the reason we ignore friction is because friction makes things difficult to calculate. So does friction exist? Well, of course it exists. But when we're introduced to the subject, we're going to ignore friction because it makes calculations easier. We do the same thing in chemistry. So we're going to look at solutions where the solvent and the solute have similar intermolecular forces. You don't have to worry about determining that. I'm just telling you right now, I will give you ideal solutions. So don't worry about anything outside of that. Okay. So here's our first example. Suppose a water sample at 25 degrees Celsius contains 0.9 moles of water and 0.5 moles of a non-volatile solute. Pure water vapor pressure is 23.8 torr. What is the vapor pressure of the solution? Okay. So really, this is a pretty simple plug and chug problem. I would say the hardest part about this problem is this mole fraction. So that's kind of new. So it's probably going to be the most difficult piece of this. All right. So just like every problem, I'm going to take inventory of what I know, try to determine what I don't know. Okay. So here's my 3 variables that are in my formula. So what is the vapor pressure of the solution? So this is pressure of solution. That's what we're solving for. I'm going to jump down here to pressure of the solvent. So that one's pretty clear. So the pressure of solvent, our pure water, is 23.8 torr. And now I just need to fill in the mole fraction. So let's come over here and do mole fraction. So again, mole fraction, specifically for the solvent, is going to be the number of moles of solvent over the total. Okay. So our solvent in this case is water. If you were unsure of that, if you didn't know, you just need to compare these two numbers. So I have 0.9 moles, I have 0.5 moles. Solvent is always the number in greatest proportion. So water is our solvent. So we're going to put 0.9 moles up here. Okay. And then the bottom is the total number. So that's going to be solvent plus solute. So that's going to be 0.9 plus 0.5. Okay. So the total is 1.4 moles on the bottom. Okay. I've got moles on top. I've got moles on bottom. So technically this idea of a mole fraction is a unitless number, which is handy because we've got pressure and pressure. We don't want that to have a unit. So I'm going to take 0.9 divided by 1.4. And I see that the mole fraction is 0.64. Okay. I've got 2 of the 3 variables. Now it's plug and chug. So the pressure of the solution is 0.64 times 23.8 torr. So the pressure of the solution equals 0.64 times 23.8 is 15.2 torr. If I teach you nothing else this semester, I want to teach you to step back and say, does this answer make sense? So one of the gifts that we have in science is this is a real life scenario, so we can logically think through it. So according to Raoult's law, this is vapor pressure lowering. So when I add the solute to this solution, the pressure should go down. So it was 23.8. It is now 15.2. That's a thumbs up. The pressure did in fact go down. That makes sense. Okay. So that is an example of Raoult's law, and that is an example of vapor pressure lowering. So here's another example. Why don't you go ahead and work through this example? So pause the video, work through it, and then I'm just going to write the answer in a few seconds. So see if you can work through it and get the right answer. Okay. So the twist in this one is you have to determine the moles of water, you have to determine the moles of glucose, and then use that in the mole fraction. So that's what made this one a little bit more difficult. I was kind and gave you the molar mass. So once you have that mole fraction, then it's just plug and chug, and the pressure does go down slightly, so it's not a big change, but the pressure does in fact go down. That's the end of this lecture. That's the end of vapor pressure lowering. I hope you guys found this helpful.